Good morning students. So last class we learned how to calculate the rate constant and also how to calculate the order of the reaction, how to find the order of reaction and half-life calculation. So up to this completed. So in this chapter the last part is the Arrhenius collision theory. Along with that, what is the effect of temperature on rate constant, effect of temperature on rate constant and presence of catalyst, what is the effect. Okay. So complete this part in Arrhenius collision theory. So the last part in this chapter, that is the Arrhenius collision theory. So what is this Arrhenius collision theory, how the reactions takes place, what is that Arrhenius expression. So the concept is the Arrhenius collision theory. For theory point of view, this is a very important long answer, and many entrance questions also they are related to this Arrhenius collision theory. So what is this Arrhenius collision theory, how the reaction takes place. So here reactants combines changes to, again chapter starting what we learned that only, reactants changes to products. So how these reactants changes to products, here number of reactant molecules. All these reactant molecules combines with each other, they changes to product. So reactants combines changes to product means here between the reactants, in reactant molecules first breaking of bonds takes place and in products formation of new bonds takes place. So before the formation of product, in reactants breaking of bonds, then in products formation of new bonds. So how this breaking of bonds takes place, collisions between the reactant molecules takes place. So according to this theory, so all these reactants are considered as hard spheres. There is a one drawback in this Arrhenius collision theory, structure not considered, just they consider as a hard spheres, okay, hard particles. Now these hard particles, nothing but reactant molecules collide with each other, collisions with each other. So because of these collisions, reactants changes to products. So how these reactants changes to product, according to Arrhenius concept, reactant molecules number of, this is based on kinetic molecular theory of gases only. So reactant molecules collide with each other. Between the reactants number of collisions takes place. So number of collisions per second takes place. Because of these collisions only reactants changes to products. So listen all these postulates carefully. The question is, the following is the correct statement with respect to Arrhenius collision theory. What are the postulates he given? So all the reactants considered as hard spheres and reactant molecules are collide with each other, collisions takes place. Because of these collisions only reactants changes to products. So per second number of collisions takes place. If all these collisions leads to the formation of products, if all the collisions leads to the formation of products, all the reactions are very fast reactions. All the reactions are very fast reactions. There is no slow reaction, there is no moderate reactions. If all collisions leads to the formation of products. So between reactants number of collisions takes place. If all collisions leads to formation of products, all the reactions are very fast reactions. No slow reactions, no moderate reactions. But most of the reactions are slow reactions and moderate reactions. Nothing but all collisions not leads to the formation of products. All collisions not leads to the formation of products. Why all collisions not leads to the formation of products? So here, this is the reaction coordinate and it is the energy, that is nothing but kinetic energy, okay, energy of the molecules. So here reactant molecules, these reactant molecules collide with each other, they changes to products. For example, the given reaction is a exothermic reaction. The reaction is exothermic reaction, endothermic reaction. Like this graph given, see this, it is the energy of reactants, energy of reactants, and here it is the energy of products. This is energy of products, this is the energy of reactants. On y-axis we are using energy and this is the reaction coordinate. Nothing but like this reaction takes place. Reactants changes to products. Reactant changes to products. Now like this reactant changes to products means the product energy is more than reactants or less than reactants? More than reactants. Products energy more means what happened? Energy gained. Energy gained means the reaction is a endothermic reaction or exothermic reaction? Endothermic reaction. Like this graph given, it is a endothermic reaction. So here all collisions not leads to the formation of product. Why all collisions not leads to the formation of product? What happens here? So here this type of graph given, it is a endothermic reaction. If the given graph is energy and this is the reaction coordinate, Now we are getting graph like this. So this is the energy of reactant, this is the energy of a product. Energy of reactants and products. So product energy is less than reactants. So what is the meaning of this one? Products energy less means reactants loses some energy, then they changes to products. Loses energy means that is the exothermic process. Now it is the graphical representation for exothermic. Anyhow in chemical equilibrium also you learn this concept. This is a graph for endothermic reaction and this is a exothermic reaction. Now what is this difference? Energy of product minus energy of reactants. Product minus reactant, delta S, delta G, delta H. This complete concept we learned in thermodynamics. So energy of product minus energy of reactant, that is equal to enthalpy of this reaction. Yes or no? This is delta H. Just they will give this is X, this is Y. Calculate the enthalpy of reaction given this difference only. Energy of product minus energy of reactants. It is equal to delta H. Enthalpy of reaction, enthalpy of reaction. So in endothermic reaction, this enthalpy of reaction is positive or negative? In endothermic, delta H is positive or negative? This product's energy is more than reactant's energy, definitely will get positive. So here delta H is a positive. If delta H is positive, that reaction is a endothermic reaction. And here what happens, say this, reactants and products, products minus reactants, products energy is less than reactants. So delta H, this is the enthalpy of this reaction. Just here like this graph, and what is this X? Here X given, that is the delta H, enthalpy of reaction. Now this enthalpy of reaction is negative or positive? So in exothermic reactions, delta H is a negative. This is a graphical representation for that. How we are taking here positive, there negative. Here delta H is a positive, there delta H is a negative. Now see this. Up to this, reactants collide with each other, then they changes to product. So this is the minimum energy that required to convert reactants to products. So this energy barrier is called threshold energy. Threshold energy. Nothing but that is the cutoff mark. So there is a threshold energy. That is the minimum energy required to convert reactants to products. This much minimum energy is required. That energy there, then this reactants changes to products. Less than this energy there, reactants not changes to products. So here all these reactants collide with each other. But which reactants have this energy, this much energy or more than this energy? Those reactants only changes to products. So here reactants changes to products. How these reactants changes to products means here breaking of bonds, their formation of new bonds. So what happens, how this breaking of bonds takes place? All the reactant molecules are collide with each other. Number of collisions takes place between reactants. All these collisions, if they leads to the formation of products, all the reactions are very fast reactions. But most of the reactions are slow reactions. What happens here? Why most of the reactions are slow reactions? So now here, to convert that reactants to products, every reactant must possess some minimum amount of energy. That energy there, that knowledge there, then only getting CT is possible. So the minimum energy, that minimum energy is called threshold energy. That is a threshold energy. But most of the reactants, less than threshold energy only there. Very few reactants more than the threshold energy, those only can changes to products. Remaining all the reactants less than threshold energy, they are collide with each other, reading, but not getting seat. Nothing but energy is less than threshold energy. So very few only highly intelligent, nothing but more than threshold energy changes to products easily. But remaining all the reactants less than threshold energy. Now these reactant molecules are normal molecules. All these reactant molecules are normal molecules. These molecules collide with each other but not changes to products. Now what happens? So now here collisions takes place between reactants, but all the collisions not leads to the formation of products. Why all collisions not leads to the formation of products? For the formation of product, the reactant molecules must contain some minimum amount of energy. That energy is a threshold energy. But here the problem is most of the reactant molecules energy is less than threshold energy. The energy is less than threshold energy. These reactant molecules collide with each other, but they are not changes to product. But here here during these collisions what happens? According to kinetic molecular theory of gases, all the molecules collide with each other. So energy transfer from one molecule to another molecule, energy transfer from one molecule to another molecule, but overall kinetic energy remains constant. This point only we learn their kinetic molecular theory of gases. So here also what happens? During these collisions, energy transfer from one molecule to another molecule. So energy transfer from one molecule, for example A collide with each other. Okay. Now here two reactant molecules. Okay. This concept only for bimolecular and elementary reactions only, not for other. This theory successfully explained bimolecular elementary reactions. Nothing but two molecules we are taking. Now these are collide with each other. What happens? Energy transfer from one molecule to another molecule. Overall kinetic energy remains constant, but one to another energy transfer. Nothing but one molecule getting more energy, another molecule energy is very less. Now here one molecule with very high energy, another molecule with less energy. Anyhow some of the molecules gaining energy, nothing but these molecules cross this threshold energy barrier. Okay. So how much energy they should gain? This much energy. This is the energy of the reactant molecules. This is threshold energy. During these collisions, these reactant molecules gains energy. If the gained energy is this much, then they cross the barrier. Nothing but reactants changes to products. Reactants changes to products. So during collisions, some of the reactant molecules gains energy from one molecule to another molecule. So some molecules cross this threshold energy barrier. Which molecules cross? That changes to product. Remaining molecules again here. That's why most of the reactions are slow reactions. Now how much energy gained here? This one minus this one. Threshold energy minus energy of the normal reactant molecules. That much energy is gained. So how much energy is required to cross this threshold energy barrier? That energy is the activation energy. That energy is activation energy. So now what is the activation energy of this forward reaction? For example, it is reversible reaction. What is the activation energy of forward reaction given? This is the activation energy of forward reaction. This much is required. What is the activation energy of backward reaction given? For example, if it is reversible reaction, what is the activation energy of backward reaction? Backward reaction, this is the reactant, this is the product. Now this energy difference is the activation energy of backward reaction. This is activation energy of a forward reaction. Now here forward reaction activation energy is more or backward reaction activation energy is more? Which is the more? Forward reaction activation energy is a more. Activation energy more means there is a slow reaction or fast reaction? Slow reaction. Activation energy is more, nothing but more energy required. So molecules, less molecules only gains this more energy. Cutoff mark is very high, so very less number of students only can get that, can cross that. Nothing but the reaction is a slow reaction. The reaction is slow reaction. Nothing but this forward reaction is a slow reaction compared to this backward reaction. Compared to backward reaction. Now here number of steps given. Where activation energy is more, that is the slow reaction. Slow reaction means rate constant value is more or less. Where activation energy is more, that is the slow reaction. Slow reaction rate constant is more or less. In rate constant, one point we learned. Rate constant, what is the application use of rate constant? It indicates the speed of the reaction. Rate constant value is more, the speed of the reaction is also more. Speed of the reaction more means the rate of reaction is more. Yes or no? This point we learned in rate constant or specific rate. Rate constant value is more, speed of the reaction is also more. Activation energy is more. Now the reaction is a slow reaction. Slow reaction means rate constant more or less. Rate constant is more, speed of the reaction is also more. Nothing but rate of reaction is more. Okay. Here activation energy is more. Nothing but the reaction is a slow reaction. Reaction, slow reaction means K value less or more. K value is less or more. Definitely K value is less, no. Slow reaction. Fast reaction, K value is more. This point we are learning. Nothing but here slow reaction, K value is less. Yes or no? K value is less. So activation energy is more, rate constant is less. Nothing but rate constant and activation energy directly proportional or inversely proportional? Activation energy is more, K value is less. So both are directly proportional or inversely proportional? EA is more, K is less, inversely proportional. As the activation energy increases, K value decreases. K value decreases means rate decreases. Activation energy increases, K value decreases. K decreases, rate decreases. Nothing but K is inversely proportional to activation energy. In 4 options, activation energies they will give, which is the fast reaction. How to identify? Where activation energy is less, that is the fast reaction. Anyhow, come to these postulates. So, what is the first one? Reactants molecules before the formation of products, all the reactant molecules are collide with each other. If all the collisions are leads to the formation of products, the reactions are fast reactions. All the reactions are very fast reactions, but most of the reactions are slow reactions. Why most of the reactions are slow reactions? Nothing but all collisions not leads to the formation of products. What happens? Why all collisions not leads to the formation of products? For the formation of product, every reactant molecules must possess some minimum energy to convert into product. That minimum energy is the threshold energy. But here problem is most of the reactant molecules have less energy than this threshold energy. That's why these reactants not changes to products. Very few reactants only changes to products. Then how this reaction total completes? How all the reactants changes to products? What happens here? Reactant molecules are collide with each other. During these collisions, energy transfer from one molecule to another molecule. So, some of the molecules possess a high energy. Now, these molecules nothing but they gained energy. Then they cross the threshold energy barrier. Then reactants changes to products. Again between these reactants, again collisions. Again that some reactions gains that energy, cross the threshold energy barrier. Then they changes to products. Like this slowly all the reactants changes to products. So, now how much energy gained by these normal molecules to cross this threshold energy barrier? Nothing but this energy minus this energy. That difference is called activation energy. Activation energy means the minimum energy is gained by the reactant molecules to cross the threshold energy barrier. That energy is the activation energy. Okay. Now, this is the activation energy. If the given reaction is reversible reaction, it is the activation energy of forward reaction. This is the activation energy of a backward reaction. Now, how to get the formula to find the delta H if forward and backward activation energies are given? Now, how to get the formula for delta H calculation? Activation energy of forward reaction given, activation energy of backward reaction given. What is the formula? Means backward minus forward, forward minus backward. Problems based on this one formula, simple formula, just subtraction only, but backward minus forward or forward minus backward, that we should decide. These problems also very important. Now here, this is a negative, positive. Endothermic reaction, this is a positive. Exothermic reaction, this is a negative, because energy of product minus energy of reactants. Here this is positive. To get this positive, activation energy of backward minus forward we have to do, or forward minus backward to get the positive value. This activation energy is more. For example, it is a 500. Okay, activation energy of forward reaction is more, and this activation energy is less. Backward reaction activation energy is less. For example, it is a 200. Now, delta H. This delta H we should get positive only, no? Delta H must be positive because given is a endothermic reaction. How to get positive? 500 minus 200, 200 minus 500. Definitely 500 minus 200. Nothing but what is the formula to find the delta H? Delta H is equal to activation energy of forward reaction minus activation energy of backward reaction. Okay, they will give activation energy of forward and backward. If you are getting confusion here, forward minus backward or backward minus forward, just you draw one graph, endothermic graph only you take. This delta H must be positive. Definitely this is the more value, this is the less value. More minus less, then only we will get the positive value. Nothing but the formula must be activation energy of forward reaction minus activation energy of backward reaction. So here the activation energy of forward reaction is X, the activation energy of backward reaction is Y, activation energy of backward reaction is Y, activation energy of forward reaction is X, and what is the delta H in exothermic reaction given? Delta H in exothermic reaction, X minus Y or X plus Y or Y minus X, like this mentioned. What we have to take? The formula is activation energy of forward minus activation energy of backward. Forward minus backward. Forward is x, backward is y. X minus y. Finally, delta H will get negative or positive. Again, question we should observe. The question is in exothermic reaction. In exothermic reaction, they are asking means definitely this is negative. This is negative means another question, x greater than y greater than x and y are equal. X greater than y greater than x and y are equal, we can't identify. Like this options given. Then delta H equal to negative. Negative we should get means definitely y greater than x. Otherwise in this graph we can see this is the activation energy of forward reaction and this is the activation energy of a backward reaction. Forward minus backward, negative value we are getting. Here backward activation energy is more than forward activation energy. Anyhow, what is this activation energy? The energy difference between the threshold energy and energy of the normal molecules, or the how much energy is gained by normal molecules to cross the threshold energy barrier to form the products. That energy is activation energy. Now some of the molecules possess this activation energy. These molecules are called activated molecules. Okay. Now these activated molecules collide with each other. Now A star collide, then it changes to product. Just A collide, not changes to product. A star, this is activated molecule, this is also activated molecule. If these two activated molecules are collide with each other, then that collision is a truthful collision. Then that leads to the formation of a product. Normal molecules collide, energy is less than threshold energy, not changes to products. So this type of collisions not changes to products. This type of collisions only changes to products. That's why very less number of reactants are changes to products. That's why most of the reactions are slow reactions. So for the formation of product, definitely the collisions must be effective collisions. Effective collisions means collisions between activated molecules, activated collisions. Okay, then only they changes to products. Sometimes these effective collisions also not leads to the formation of product. Nothing but formation of product depends on one more factor. Formation of products depends on one more factor. So what is that another factor? Very simple, see this, reactants collide with each other. Collide, not that collide, not LLOI. That is a collider solution. This is a collide, nothing but collisions. Reactant molecules collide with each other. But all collisions not leads to the formation of products. Not leads to the formation of products. Why not leads to the formation of product? So minimum energy is required to form the products. That minimum energy is called threshold energy. But problem is most of the reactants have less energy than minimum energy. Less energy than this threshold energy. Those molecules are called normal molecules. What are the postulates? What are the correct statements according to this Arrhenius collision theory? Okay. So first they consider as hard spheres, then these collide with each other, but all collisions not leads to the formation of product because they must contain some minimum energy. That minimum energy is a threshold energy. Most of the reactants are initially normal reactants, normal students, but after vigorous practicing only they changes to top students. So less energy. So these are normal molecules. Now these normal molecules collide with each other. During these collisions, energy transfers. Energy transfers. Some molecules gains more energy and they cross the threshold energy barrier. Cross threshold energy barrier. After vigorous practicing, some students gain up, but some students as it is there. So now here some are activated molecules, remaining molecules in normal stage only. Now these activated molecules collide with each other. Now special preparation, collide with each other, then it leads to the formation of products. Leads to the formation of products. So how much energy gained? That energy is called activation energy. So what is the formula for this activation energy? Activation energy is equal to threshold energy minus energy of the normal reactant molecules. That difference is a gained energy, that is the activation energy. So now these molecules are called activated molecules. Collisions between these activated molecules are called activated collisions or effective collisions. These effective collisions only leads to the formation of products. Effective collisions leads to the formation of products. But one more factor also affects this collision, nothing but formation of product. What is that? Another factor. So why reactions are very slow means very slow, very less number of molecules are activated molecules. What is the another factor? So here we are using CH3 Br. Okay, CH3Br, name methyl bromide. Methyl bromide. It is treated with OH minus. OH minus. Now Br minus replaced by OH minus. Br minus replaced by OH minus. The reaction is a nucleophilic substitution reaction. Organic nucleophilic substitution reaction. This is the Br minus replaced by OH minus. Negative species is called nucleophile. Now this is a one nucleophile replaced by another nucleophile, means the reaction is a nucleophilic substitution reaction. Now these two approach like this. Okay, no reaction takes place. There is no reaction. But here this OH minus from backside approached. Here Br, like this one molecule is there, OH minus approached this molecule in this direction. There is no product formation. But OH minus approached from backside. Okay. Now here slowly bond formation takes place. This bond becomes a weak. Here bond becomes a weak and here bond formation started. After some time this becomes a strong bond and this Br minus eliminated. Br minus eliminated. What happened? Br minus replaced by OH minus. So the reaction is a nucleophilic substitution reaction. If OH minus approached in this direction, there is no product formation. But OH minus approached in this direction, then here bond formation started, it becomes weak. Here one intermediate we are getting, that is the intermediate activated complex. This is activated complex. Fraction of seconds only it exists, immediately decomposes. So anyhow an intermediate complex is formed. Then finally this one eliminated, here strong bond formed. Now this is the product. So Br minus replaced by OH minus. When this product formation takes place, this is activated molecule only, but both are collide. This is activated molecule, this is also activated molecule, both are collide with each other, but not changes to product. Why not changes to product? Orientation is not in proper direction. So the formation of product also depends on orientation factor. Orientation factor means from which direction there is the bonding. Okay, orientation factor. So from this direction bonded, then only bond formation takes place. So here formation of product depends on effective collisions. The collisions must be effective. Minimum energy is required. Energy only not sufficient. One more is there, that must be approach in proper direction. Proper direction means there is the orientation. So formation of products depends on effective collisions and also depends on orientation factor. Orientation is also in proper direction there, then only formation of products takes place. That's why very few reactants only changes to products. So most of the reactions are very slow reactions. Why most of the reactions are slow reactions? Minimum energy is required. After gaining energy also proper direction is not there, then no formation of products. So anyhow finally formation of product depends on energy of the molecules and also depends on orientation of the molecules. So two factors mainly affects. One is effective collisions, another is orientation factor. So if the orientation is also correct, orientation correct, then only it leads to the formation of products. Okay. So it's the Arrhenius collision theory, how the reactants changes to products. Why most of the reactions are slow reactions? Why most of the reactions are slow reactions? So here initially reactants are collide with each other. All the students are joined in college and all collisions not leads to the formation of products. Just joined in college not get the seat. And next, so to get the seat some minimum amount of energy is required. That energy is a threshold energy. But most of the students are less energy than this threshold energy. So these molecules are, these students are called normal students. Now these normal students started preparation, then some students gains energy, gains knowledge. Now those students are called activated students. Now these activated students are separated and more preparation, vigorous preparation started. Vigorous preparation, then that is the activated collisions. These activated collisions leads to the formation of product. Just vigorous preparation in one room, very top students kept, that rank getting is not possible. Proper direction also required, like this. This period you have to prepare this 1 hour like this, 1 hour like this, the direction also required. So for the formation of products, for getting that rank or seat, definitely orientation also required. So it depends on orientation of the reactant molecules and also depends on effective collisions. So that's why most of the reactions are slow reactions. Very few reactants only changes to products. Okay. So how the reaction takes place? This is the Arrhenius collision theory. So now what is the expression for this Arrhenius collision theory? Rate. It depends on now come to the rate. Rate depends on number of collisions takes place in unit volume in unit time. Number of collisions takes place in unit volume, because of collisions only reactants changes to products. So number of collisions takes place in unit volume in unit time, that is called collision factor. Collision factor. So here this is represented by Z. Collision factor, because of collisions. But these collided molecules must possess some minimum energy, that is the activated energy. Activated energy there, then only that leads to the formation of products. So here number of molecules with activation energy, that is represented by e power exponential minus Ea by RT. Ea by RT. This is the Boltzmann factor. Boltzmann factor means fraction of the molecules with activation energy. Z is the collision factor. Collision factor means how many collisions takes place in unit volume in unit time. How many collisions takes place, how many molecules with activation energy. So rate depends on this number of collisions with activation energy. Number of collisions with activation energy. So rate is equal to Z into e power minus Ea by RT. This is called Boltzmann factor. It is nothing but fraction of molecules with activation energy. Fraction of molecules with activation energy. But this also depends on orientation of the molecule. Orientation also required. So orientation factor, that is represented by P. So P into Z into e power minus Ea by RT. This P and Z combinedly Arrhenius given A. Now this is the Arrhenius factor. Just simply it is the Arrhenius factor, Ae power minus Ea by RT. Rate constant. So K is equal to Ae power minus Ea by RT. It is the expression for Arrhenius collision theory. So K, Arrhenius equation. So what is that Arrhenius equation? K is equal to Ae power minus Ea by RT. Or this one given, these two also correct. Rate is equal to Z into e power minus Ea by RT, or it is the P Z into e power minus Ea by RT. Combinedly this we are taking as a Arrhenius factor, A into e power exponential minus Ea by RT. So K is inversely proportional to activation energy and directly proportional to temperature. So Arrhenius only explained the effect of temperature on rate constant. What is that effect of temperature? For every 10 degrees raise in temperature, the rate constant value double or triple. Yes or no? That is only temperature coefficient. What is the temperature coefficient? K at T plus 10 degrees by KT. It is equal to 2 or 3. Using this, some problems also there, no? Initial temperature is 10 degrees centigrade and now the temperature is 60 degrees centigrade. K how many times increased? So generally 2 or 3, not mentioned, 2 only we have to take. Every 10 degrees raise in temperature, the rate constant value is double. So rate constant double means now 10 degrees changes to 60 degrees. Nothing but how many times? For every 10 changes to 20. Double, changes to 30, double, changes to 40, double, changes to 50, double, changes to 60, double. So how many times? 2. Yes or no? So rate constant for every 10 degrees double or triple, that is the temperature coefficient. So rate constant is directly proportional to temperature, inversely proportional to activation energy. So for every 10 degrees raise in temperature, rate constant value double. So one best example for this, anyhow in practical you did that, that is the KMN4 with oxalic acid titration, KMN4 versus oxalic acid. Any indicator used? Autocatalysis, Mn plus 2 acts as a self indicator. In surface chemistry also we learned Mn plus 2, one of the product acts as a catalyst for this, one of the catalyst, no, that is a catalyst, and indicator KMN4 colored. So special indicator not required, KMN4 only acts as a indicator. So in that oxalic acid reaction, what happened? First 10 ml oxalic acid pipetted out into one conical flask. Remember, no, this experiment. So volumetric analysis, titration. Okay, so 10 ml that oxalic acid pipetted out into one conical flask, then one full test tube, nothing but 10 ml or one full test tube, that is a 10 ml only, no, 10 ml concentrated sulfuric acid we have to add this, then we should titrate with the KMN4, but before that we have to heat, just bubbles should come, so we have to heat 5 to 10 minutes. Why we should heat? If temperature increases, rate of reaction increases. Without heating direct you started, that reaction is a slow reaction. After heating the reaction speed increases, that's why we are heating that oxalic acid present in conical flask. Otherwise 2N2O5 gives 2NO2 plus O2 reaction, there no, first order, second order. 2N2O5 gives 2NO2 plus O2, first order or second order. 2H2O2, already I think based on this last Sunday exam completed. So 2N2O5 gives 2NO2 plus O2, that is a first order reaction, bimolecular but first order reaction. Nothing but pseudo first order. No, pseudo first order means one of the reactant taken in large excess quantity, that is called pseudo first order. So it is the first order reaction. At 0 degree centigrade given, the reaction, that reaction requires a 10 days time to complete the decomposition of N2O5 at 0 degrees. 25 degrees centigrade given, it requires 1 hour, 2 hours like that type. But 50 degrees centigrade temperature maintained, that reaction completes in 10 minutes, 20 minutes like this. Nothing but what happened here? Temperature increases, speed of the reaction increases. So as the temperature increases, rate constant value increases. Why speed of the reaction increases? As the temperature increases, speed of the reaction increases. Why speed of the reaction increases? Kinetic energy of the molecules increases. Yes or no? Kinetic energy directly proportional to temperature. Temperature increases, kinetic energy of molecules increases. Most of the molecules with activated energy, number of activated collisions increases. Number of activated collisions increases, rate of the reaction increases. Nothing but this one explained by Arrhenius. Arrhenius explained the relation between rate constant and temperature. So as the temperature increases, kinetic energy increases. So for this graphical representation, just here we are taking fraction of the molecules with kinetic energy. Fraction of the molecules with kinetic energy. So here very less molecules least kinetic energy, very less molecules highest kinetic energy also. Most of the molecules this average kinetic energy there. Most of the molecules this average kinetic energy. This is the most probable kinetic energy. Okay, most of the molecules like this. Now at two different temperatures mentioned, fraction of molecules, kinetic energy at temperature now see this one, fraction of molecules, okay, and it is the kinetic, this is E, kinetic energy, okay. This is activation energy. For example, if this energy barrier crossed, then they changes to products, these reactants changes to products. Fraction of the molecules at temperature T, this is the temperature T plus 10 degrees centigrade, T plus 10 degrees centigrade. This is the graph at temperature T. Most of the molecules before this activation energy only, before this activation energy, nothing but these reactants not changes to products. Which reactants changes to products? This fraction changes to product. this fraction of the reactant molecules only changes to products, because this is the energy increasing like this. This is activation energy. So how many molecules cross this activation energy? They only changes to products. This much fraction changes to product. Okay. Now temperature T plus 10 degrees, 10 degrees raised. Now what happens? See this. Most of the molecules high kinetic energy, because this is the kinetic energy, less kinetic energy is less, most of the molecules high kinetic energy. Now this much molecules cross the activation energy barrier, nothing but this total changes to products. So now it is doubled, yes or no? Doubled. So the fraction of the molecules cross that activation energy barrier, double or triple. Nothing but for every 10 degrees rise in temperature, the rate of reaction is double or triple. That ratio is only called temperature coefficient. So Kt plus 10 degrees by Kt, that is equal to 2 or 3. Anyhow, what is the effect of temperature? As the temperature increases, kinetic energy of molecules increases. Most of the molecules can cross that activation energy barrier, and most of the molecules can changes to products, and nothing but rate of reaction increases. So as the temperature increases, rate of reaction increases. So K is directly proportional to temperature and inversely proportional to activation energy. Now this is in exponential form. Convert into logarithm. What we can write? Now Arrhenius equation, K is equal to A e power minus Ea by RT. Okay. Now it is ln K is equal to minus Ea by RT plus ln A. Yes or no? We are converting that exponential form into natural logarithm. It is a ln K is equal to minus Ea by RT ln A. Here any y equal to mx plus c, y equal to mx form getting? Y mx plus c. So on y axis what we can take? Now graphical representation. This graph is very important. Graphical representation for Arrhenius collision theory. On y axis what we are taking? ln k. Okay. On x axis minus Ea by R, and this is a 1 by T. 1 by T. Nothing but K versus temperature effect. Okay. Now we are taking 1 by T. Arrhenius collision theory explains the effect of temperature on K. For that graph we are taking. So ln K 1 by T, not T, 1 by T. If direct K and T given, as the temperature increases, K value increases. Yes or no? Like this. Now given is a ln K 1 by T. Okay. Now negative slope or positive slope? Minus, very simple, y equal to mx plus c. On y axis ln K, on x axis 1 by T. Now what is that? M minus Ea by R, negative slope. So negative slope we are getting. Slope is equal to minus Ea by R, minus Ea by R. Intercept is equal to ln A. So it is a graphical representation for this Arrhenius equation. ln K versus 1 by T, negative slope. Here T given, 1 by T given, observe that 1 by T given. That's why like this negative slope. Slope is equal to minus Ea by R, and intercept is equal to ln A. Now convert this into log base 10. Log base 10. So what is the formula? 2.303 log 10 K is equal to minus Ea by RT plus 2.303 log A. Okay. Now can we divide full this with 2.303? 2.303 divide. Then what will get? Log base 10K, divide the whole equation, minus Ea by 2.303 R, yes or no, plus log base 10 A. This is a T, RT also there, RT, okay, Ea by 2.303 RT. Now it is a y equal to mx plus c form. Again this is y equal to mx plus c form. On y axis, so carefully we should observe, on y axis ln K given, log K given. Now log base 10 K versus 1 by T. Now also negative slope. Here slope is equal to, just they will give the slope value, calculate the activation energy. Can we calculate activation energy? So slope is equal to minus Ea by 2.303 r, okay, minus EA by 2.303 r, and intercept is equal to log A. So log K given, slope is equal to minus EA by 2.30. Options EA by r or EA by 2.303 r, or minus plus. So it is the negative slope. Here ln K, here we are using log K. Okay. Now log K2 by K1 is equal to, like that given. Now come to this. This is better. If it is ln K1 at T1 temperature, okay, K1. Now ln K2 minus EA by RT2, full derivation not required. Finally one formula there, that formula we are going to use in different problems. So ln A, this is at T2 temperature. Now K2 by K1 we want, then what we should do? Minus, because it is a logarithm, ln K2 minus ln K1, ln K1 minus ln K2, ln K2 minus ln K1, okay, ln K1 is equal to this minus this minus this, nothing but this one cancel out, yes or no, remove this. So what we are getting? Minus EA by RT2 minus of minus EA by RT1, yes or no, RT1, nothing but it is ln K2 by K1, this is K1, ln K2 by K1 is equal to minus EA, remove this minus here, EA by RT1 minus EA by RT2, minus of minus plus no. So EA by RT1 minus EA by RT2. Now EA by R, take common, EA by R, 1 by T1 minus 1 by T2, or 1 by T2 minus 1 by T1. So this is a 1 by T1 minus 1 by T2, okay. Now convert this ln into logarithm, log base 10, natural logarithm to log base 10. 2.303 log base 10 K2 by K1 is equal to EA by R into T2 minus T1 by T1 T2, yes or no, shift this 2.303 this side. So log base 10 K2 by K1 is equal to EA by 2.303 R. So problems based on this, they will give activation energy T1, T2, we have to calculate any one K1 they will mention. Problems based on this very important. It is the Arrhenius equation. Effect of temperature on rate constant. So log K2 by K1 is equal to EA by 2.303 R into T2 minus T1 by T1 T2. They will mention temperature initial and final, activation energy, and K value just double, triple or quadruple. Quadruple given means how many times quadruple? Double 2 times, triple 3 times, quadruple 4 times. 4 times increased, and now calculate that activation energy or like that, okay. So it is the effect of temperature on rate constant. Expression for that, log K2 by K1 is equal to EA by 2.303 R T2 minus T1 by T1 T2, and graphical representation, okay. This is about Arrhenius collision theory and effect of temperature. So next small concept there is the effect of catalyst and also concurrent reactions, consequent reactions. These two reactions not in syllabus, but anyhow some problems are there to solve those problems in different materials. To solve that, just a brief explanation for concurrent reactions and consecutive reactions. These small topics are tomorrow class. Along with that, tomorrow NCERT textbook discussion. Okay, so tomorrow you have to keep with you NCERT textbook. Okay, thank you.